Hi, I'm Brian Mullen, and this is Balls Out Physics, episode 1.1, A Spinning Atmosphere. Now, I just noticed the other day that my very first video, Balls Out Physics, episode 1, Planes Flying on a Spinning Ball, was reposted on another channel on November 6th, and since then, it's gained over 250,000 views. Now, that's surprising. I don't know how that works, but it's awesome because it gets people thinking about this problem. When I first started looking into the idea of a rotating Earth and really thinking about that and applying it to the everyday world I see, one of the first things I thought about were planes flying above a spinning Earth, and I talked about that in that video. And I couldn't really find, actually I couldn't find any type of relativity problem that used planes and a moving Earth. Now, there's tons of relativity problems out there showing trains and cars and other things that are moving on a surface that is assumed to not be moving, but there's nothing that takes into account, at least since I haven't looked since then, that accounts for an Earth moving with the planes. Now, if you scroll through the comments on that video, I posted a link to where my video has been reposted. People saying the same thing that even I said, is, of course, the air slows the plane down, because my argument was an object in motion stays in motion unless acted upon by an outside force. So what's slowing the planes down? Because I said the atmosphere, I didn't make the statement, which I should have done, about my assumption of an atmosphere spinning with the Earth. How can that be? And so I implied in the video that why aren't the planes going into orbit? Okay, now we know in this reality that planes slow down because of air resistance. That's obvious. The whole point of that episode was to get people thinking about it so we can try to explain this. And so this video is about the concept of a spinning atmosphere and why I have a lot of trouble with it, and really why I ignored the spinning atmosphere in my very first episode. So let's say we're looking down on the North Pole of the globe Earth, and the Earth is rotating, spinning, or I should say rotating. People have given me some criticism for I should say rotating instead of spinning, because they said it's being deceptive to say spinning, but I mean spinning, rotating, I really think it's the same thing. So anyway, Earth is rotating, right? And so let's say we're going to freeze the Earth at that moment. Freeze the Earth with the atmosphere around it, assuming that the atmosphere is rotating with the Earth. And that's what I have drawn on the board here. Okay? So here's the Earth down here. All right, and let's say that this line right here is the equator. When you're looking down on it, the equator is right here. Okay, so we're just going to say this line is the equator, and then this is the edge of the atmosphere up here, and then there's space out here. Now, this is obviously not the scale. This is just conceptual. Okay, and so at the equator, the circumference of the Earth is roughly 25,000 miles. And so to figure out the instantaneous velocity of the Earth as it spins around its axis on the equator, you divide the circumference by the time it takes to make one revolution, which is 24 hours. And when you do that, you get roughly 1,038 miles per hour. Okay? And so we assume right here that this is the Earth rotating at 1,038 miles per hour. And I said in the video, and people have said in the comments, that you can just say that that's zero. Okay? And so what I want to do is look at this atmosphere and look at 3 points and 3 elevations, okay? A, B, and C, and assume that we're looking at just 1 cubic foot of air, okay? Just to get our minds around this volume of air that's frozen in time right now, okay? So all of it's moving, all the air is moving with the Earth in such a way that it appears relatively stationary. You know, we go outside, wind blows and moves around, but it's all moving with the Earth, and that's what slows the plane down, because the atmosphere moves with the Earth, okay? So point A, point B, and point C, all moving with the Earth. I mean, they could be blowing this way, they could be blowing down at this moment, but since we froze them, we know that it's all moving with the Earth and not getting left behind, right? That's the assumption. And so we will say at this moment we expect all of these points of air to make one complete revolution and come back to the same spot in 24 hours, right? Because the atmosphere moves with the Earth. The atmosphere never gets left behind. So right off the bat, since we know the velocity is equal to distance divided by time, we can say that VA, the velocity of point A, is greater than the velocity of point B, which is greater than the velocity of point C. Because point A has a longer distance to travel in 24 hours than point B, and point B has a longer distance than C, because the circumference of their path is greater, right? So I've got A up here at the edge of the atmosphere, space up here, B right here around 6 miles where planes fly, and C near the surface of the Earth, okay? And so this rotation here, the theory is that the Earth is rotating about its axis because of the Big Bang. When you really think about it, there was this Big Bang, everything exploded out into space, planetary systems formed, galaxies, all that stuff formed, and this rotation is what is left over from that explosion. That's leftover energy from that explosion of the creation, which created everything, right? And so everything's just been moving for billions of years, and there's no friction between space and the atmosphere, right? Because there's nothing in space, so an object in motion stays in motion unless acted upon by an outside force, right? But that's kind of strange when you think about that air at higher elevations has to be moving faster to keep up with the ground below it, because air moves up and down, right? Hot air rises, as we know, and cool air sinks, right? So how does the air speed up? When it's heated, it rises, but then it has to start moving faster. Now, even if it's only a little bit faster, the difference in these velocities, if you calculate them, isn't much, but they do have to be greater, or they will start to get left behind. So, how that is explained, I don't know. I haven't really found anything to talk about how the air has to be moving faster. But another thing to think about is, air isn't stationary like we're assuming in this problem, right? It blows, it moves all over the place, and down here at the surface, air goes up and down over valleys, and air actually speeds up as it goes up and as it goes over the top of a hill. It speeds up, it slows down, runs into mountains, goes through trees. There's things flying around in the air, different pressures. All kinds of stuff is happening internally as it all moves with the atmosphere. Now, I would think that eventually something's going to have to give it a nudge to keep it moving with the Earth, so to say. The energy would be lost, okay? But not to mention that, there are things that enter our atmosphere. There's meteors, all kinds of stuff is constantly is supposed to be entering the atmosphere from outer space. So that is pushing back on the atmosphere and wanting to slow it down. And so the common explanation for how the atmosphere keeps up with the surface of the Earth is by friction between the air at the surface. Let me use a red marker for this. There's friction here pushing back on this cubic foot of air down here that's at the surface. And then that's transferred through internal friction, for internal shear forces within the fluid, because air is essentially a fluid, okay? It has viscosity, and so these internal shear forces are transferred all the way up throughout the layers of air, right? Just the air pushing against itself, the friction carries that force all the way up to keep the atmosphere moving with the Earth, right? Well, the problem I have with the thing doesn't make sense to me, and this is why a lot of this is why I ignored it in the first episode, though I didn't explain it, is when you create friction, you create heat. You rub our hands together. It's actually kind of cool here today. Rub my hands together to warm them up. That creates heat. Heat is essentially kinetic energy. And so when something creates heat on the Earth, or when the Earth is heated by the sun, where does that heat go? Well, if you watch Balls Out Physics episode 4.1, I talked about how the accepted explanation for how things don't just get hotter and hotter and hotter is that it radiates out into space, right? So heat from the Earth radiates out into space, into infinite space, and that's lost forever. So this process right here, this friction process, the shear force process, creates heat, and that heat is escaping. Therefore, this whole system would be losing energy, wouldn't it? And so we say that heat is really kinetic energy, and kinetic energy is equal to 1/2 mass times velocity squared, right? And so this kinetic energy, I assume, is going down. The kinetic energy of the atmosphere is going down because it's losing heat. And since I hope we're not losing mass to infinite space, not losing our air, that leaves only velocity to go down. So not only does the speed of the air relative to the surface of the Earth have to increase as you go up in elevation, because the path it has to travel, the length of the path, the circumference, increases. We also have this problem with losing energy. I don't understand how this could work. And that's one thing I've been thinking about. I hadn't really come up with a way to explain it until making this video. So how does this atmosphere keep up with the Earth? And this is why in the very first episode I really was saying, how do planes not go into orbit? Because how does the atmosphere, in a sense, keep up with the Earth? I probably should have made this video first. So that's how I feel about this. Please keep the discussion going. I'm going to post a comment on the repost of my first video saying that I made another video to keep this discussion going, because that's what this is all about. It's just talking about this world. And if you agree with my analysis, or you don't, or you just want to keep the discussion going, please go to the video. I posted a link in the description below, and like my comment so it'll get bumped to the top so people can see this video, and then we can keep this going to figure out what's going on here. Because really this increase in velocity that you have to keep up with the Earth doesn't make sense, and then the heat loss to me. Another thing a lot of people have said is you can set the velocity of the Earth equal to 0, right? Because of relativity, we just say that the Earth isn't moving for the plane problem, right? But if VC, right at the ground surface, is roughly 0. I mean, it is a little bit above the surface, so it would have to be slightly faster than 0 because its path is slightly longer if you go to the center of a foot. That's just getting too far into it, though. So if we say VC is 0, then VB and VA both have to be greater than 0 to keep up with the Earth, or they'll get left behind in 24 hours. So how does it all work? How do these things blow and move all over the place but still keep up with an Earth that's rotating? How does that work? There's just too much going on. It doesn't really make sense for all this movement to be happening, but us to go outside and experience this relatively stationary air that we experience every day. So that's my thoughts on this. Please keep the discussion going, and until next time, peace.